In this lecture, we are going to start talking about decomposition in optimization problems. So in order to do that, we address this in two categories. One, decomposition for linear optimization problems, and one for decomposition in nonlinear. Before starting that, let's start with some motivations for decomposition of optimization problems. So in real world scenarios, there are very large scale problems that involves several variables. This leads to complexity of the solution algorithm, and sometimes it takes time to solve the problem. So how can we address this issue is we can break the large scale problem into smaller subproblems. So instead of solving your optimization problem in one location or solving a larger scale problem once, we break it into a smaller subproblems. So subproblem 1, subproblem 2, and so on. And then you assign each of these subproblems to a local entity. If I want to provide an example, let's say you have a group of robots that want to do a mission, let's say firefighter robots. And these robots want to make a decision to find the optimal strategy for controlling the fire. So there are two strategies. One is to communicate with all of these robots, receive their information, and solve a complicated problem that can find the optimal strategy for these robots. The other one is to distribute this computing, distribute this decision making among these robots, and allow each of them to solve a part of this optimization problem. But then it's not just assigning these tasks to each of the local entities, it's also about coordination among entities. Why do we need coordination? In order to make sure that the obtained solution is optimum for the entire group of entities, rather than each of these entities solve their own local problem without having information about others. So let's try to tackle this in a form using the formulation. All right. The very first definition that we deal with in decomposition is coupling constraints and variables. All right. So usually when we want to decompose the problem, we are interested in a separable or decomposable structure. What does that mean? For example, for our objective function, if your objective function is f of x, we are interested in showing the objective function in terms of different components. Let's say f1 of x1 plus f2 of x2, and so on. So as you can see, each of these components can be decomposed without having overlap or joint variables with others. It's the same for constraints. But for constraints, we have two types of constraints that can be separable. In this case, we call them non-complicating constraints. These constraints usually engage variables only from one of the subproblems that we define. We also have complicating constraints. So complicating constraints are the challenging part of decomposition because they involve variables from multiple subproblems. Variables from multiple subproblems. All right. So this is one type of coupling, and the other type of coupling are coupling variables. So what are coupling variables? Coupling variables. Coupling variables are the variables that appear in multiple constraints. So if a variable appears in multiple constraints, we refer to it as coupling variable. So these are very basic definitions. Now that we move forward, we will see it in practice for decomposition in linear programming. All right, so decomposition for linear program. All right. The very good point about linear programming is the structural objective function is always decomposable because it's fully linear and you can decide which of the variables you want to assign to which of the subproblems. Let's say my problem is represented as minimizing x1 to xn. The objective function is j from 1 to n, cj, xj. So cj's are the coefficients here. And then subject to the non-coupling constraints, we represent them as E sub ij, xj is equal to fi, which are constant values. So we assume that we have q non-coupling constraints. And then we have some coupling constraints, j from 1 to n, aij, xj is equal to bi, I from 1 to n. This is the set of our coupling constraints. And we know that our variables are positive and they're bounded by the maximum value. All right. Now I want to try to show this in a more graphical way. So this is our objective function. Let's say we want to break our objective function into 3 components. I call the first part C1. So these are the coefficients of the first component, coefficients of the second component, coefficients of the third component. What does this mean? It means we break this into 3 parts. C1 multiplied by x1. So x1, for example, could be x1, x2, x5 plus C2, x2. So x2, for example, could be x6, x7, x9 plus C3, x3. So x3 is x10 till xn. So I somehow want to break this problem into 3 different subproblems and then try to solve this using decomposition. So this is about our objective function. Then we have the structure of constraints. So for constraints, we have the same story. This is for non-coupling or non-complicating constraints. For non-complicating constraints, the coefficients are also separable. So we have E1 that refers to first set of variables or first subproblem, E2 for second subproblem, and E3 for third subproblem. As you can see, E1 corresponds to the first set, E2 second, E3 third. We also have complicating constraints. So these are our complicating constraints. We call this coefficients A. For complicating constraints, as we expect, there are coefficients for all of the sets in the same row. So which means all of the variables are engaged at the same time. All right. This is going to be multiplied by the vector of variables, which is x1, x2, and x3. And then we will have the right-hand side. So what's the right-hand side? We have f's and we have b's. So we have f1, which is for the first subproblem, f2, second subproblem, f3, third subproblem, and b for the complicating constraint. All right. Now the question is how to solve this using decomposition algorithms. Before moving to that, let's take a look at another structure when we have coupling variables. So for the case of coupling variables, what I'm going to do, I'm going to represent the problem in a different way. So coupling variables. So I want to represent the problem using minimizing sigma dj by j plus sigma ci xi. So we have y1 to yn and x1 to xm. This is j from 1 to n. This is I from 1 to n. This is subject to sigma elj, yj, j from 1 to n, plus sigma I from 1 to m, a li xi is equal to bl. L is from 1 to q. And we also know that xi's are positive and they are upper bounded by xi up, I from 1 to m. We know the same for y's. Yj, they are all positive and upper bounded by yj up, j from 1 to n. All right, so let's take a look at the graphical representation for this one. All right, so the way that it works, it's going to be vector d and vector c. So what I'm going to do, I want to decompose the first part of the problem using the same structure that we had before, because we talked about some parts of the problem are decomposable, some parts are not. So here we want to consider xi's as the coupling variables. All right, so let's decompose this to d1, d2, and d3. All right, here is how the new structure will look like. So we have the first part, E1 that corresponds to D1, E2 that corresponds to D2, and E3 that corresponds to D3. So this is for the decomposable part of the problem. But now the issue is we have coupling variables. These coupling variables, let me have this C here. Coupling variables, the coefficients are A1, so I'm talking about these coefficients now. A1, A2, and A3. All right. So we have Y1, which is non-coupling variable, Y2, second set of non-coupling variable, Y3, third set of non-coupling variables, and we have X, which represents the coupling variables. At the right side, we have right-hand side, we have B1, B2, and B3. All right, so if we want to show the set of variables here, let's say this is all of our variables, all variables. One part is Y, and the other part is X. X variables are coupling variables, but Y's are non-coupling because we could break them into Y1, Y2, Y3 without having issues of having these variables in multiple constraints. All right, now the question is how we can decompose these problems. What are the decomposition algorithms for solving such problems? Let's get started with one example in which we have coupling variables. So this is the general problem. Say minimizing Cx, variables are x, subject to E, which is a matrix, multiplied by x, which is all variables, is equal to vector f. And Ax is equal to b, and all x's are between 0 and the upper bound. All right, now we want to break this into our subproblems. So this is our original problem. Let's say this is vector x, vector x. We want to break this vector into our subproblems. So this is subproblem 1, subproblem 2 variables, and subproblem R variables. Please note that each of these subproblems could have more than one variable. For example, x1 could be x1, x2, x3. x2 could be x4, x5, x6, x7, and so on. So we break the variables into a smaller set of variables. And now we want to show this problem in the decomposable structure with this new notation. So this is the notation that we are going to use. So z is equal to sigma k from 1 to r, which is number of subproblems, ck transpose, which are the coefficients for the case subproblem, xk, the variables for the case subproblem, subject to ek xk is equal to fk, again for k from 1 to r. So what are these? These are the non-coupling constraints. Why we call them non-coupling? Because as you can see, they only engage variables from one of the subproblems. And for each subproblem, we have a set of non-coupling variables, non-coupling constraints. And then we have the coupling constraint, k from 1 to r, ak, xk is equal to b. Why do we call this coupling or complicating constraint, because as you can see, it involves variables from all of the subproblems. So that's the reason for coupling all of these variables together. And then we have the last constraint, which is all the variables for each subproblem are positive and upper bounded by their maximum value. All right. So this is the new formulation that we will use for linear decomposition. Something else that now that we have this structure, something else that I want to talk about is how we can show this graphically. Because we talked about the graphical representation, I want to just review that again to show how we can show this in a graphical way. So let me remove this part. All right. For the graphical representation, this is your objective function. So you break the variables. You have coefficients for first subproblem, coefficients for second, and coefficients for our subproblem. For the constraints, we have non-complicating. So this is E1, E2 for second, and so on. ER, the coefficients for the R's non-complicating or non-coupling constraint. And we have one constraint or one set of constraints that have variables involved from all of the subproblems. And then we multiply this by x1 from subproblem 1, x2 from subproblem 2, xr from subproblem r. The right hand side is going to be f1, f2, fr, and b. All right. So, and if you want to show this in how we want to implement this, so you have this original problem, and this original problem is going to be solved using assigning variables to each subproblem. So this is subproblem number 1. For subproblem number 1, we know that the coefficients in objective function are C1. The constraint is E1 multiplied by x1 is equal to f1. The second one, coefficients C2, constraint E2, x2 is equal to f2, and so on. Last one, CR, the constraint ER multiplied by XR is equal to FR. All right. So in this lecture, we talked about the motivations for decomposition algorithms. Why are we motivated to do decomposition? Is to facilitate, to expedite the way that we want to solve a large scale problem. So instead of solving a large scale problem, we break it into a small subproblems. Subproblem 1, subproblem 2, and subproblem R. And then we coordinate among the subproblems to make sure that the answer that each of the subproblems is obtaining is going to be optimal for the entire system. Then we talked about coupling or complicating variables and constraints. After this, we started the introduction to decomposition in linear optimization. In the next lecture, I'm going to talk about one of the decomposition algorithms for linear optimization. That decomposition algorithm is called dantzig-wolfe decomposition, and it's going to be very effective, specifically when we have coupling constraints.